Welcome to the fourth week of Statistics in Medicine. Congratulations on making it through the tricky week on probability. That was one of the harder units of the course, so I hope you found it to be fun as well as challenging. This week's builds on what we did last week. So last week we talked about calculating probabilities. This week we're going to talk about probability distributions. That is when you have the probabilities of all the possible outcomes. Related to that, we're going to talk about expected value and variance. Those concepts are very similar to what we did in week 1 when we calculated means and variances. I'm also going to talk about two specific probability distributions that are very important in statistics, the binomial and the normal distributions. So the first teaser for this week goes back to the lottery. We started talking about the lottery last week. It's a great problem when you're talking about probabilities. So in 2012, there was a particular lottery called the Mega Millions lottery that had gotten up to a jackpot, a record jackpot of $656 million. Now you could take that spaced out over 30 years, or you could instead take an immediate payout of about $500 million, but still a huge jackpot. And I received a question over email. The person asked me if the odds of winning the Mega Millions is 1 in 175 million. So notice that the Mega Millions is a different lottery than the one we talked about last week. The odds are even worse for the Mega Millions. And we're going to just assume that the probability that they've calculated there and given on the Mega Millions website is correct. So if the odds is 1 in 175 million, is there a significant statistical advantage in playing 100 quick picks rather than 100 tickets, buying 100 tickets? For $500 million with a B dollars, it almost seems worth it. So this person was asking me whether or not it would be worth it to shell out $100 because the jackpot is so big. And we're going to actually answer this question in an upcoming module. It turns out to be a really fun and interesting question to answer. The second teaser for this week is also a practical problem, but it's a little bit more on a serious note. So imagine that you are in a resource-poor area and you want to screen the population for a particular disease. So for example, maybe you want to screen all pregnant women for HIV. But for the area that you're in, the antibody test is so expensive that it actually is prohibitively costly. It's too expensive to screen everybody. So people have come up with all sorts of clever strategies in this situation. One of them is to pool the blood from multiple samples. So how this works is whenever you take a blood sample, you set aside half of that person's blood. And then you take the other half and you pool it with a group of people that you're screening. The antibody test, assuming that antibody test is sufficiently sensitive, it can pick out from the pool if anybody in that pool is positive for the disease. If somebody is positive for the disease, then you'll have to go back and test each of the individual vials of blood to figure out who actually has the disease. But imagine if it's a reasonably rare disease, a lot of the times that pool is going to come back negative. If it comes back negative, then you can assume that everybody who was included in the pool is negative for the disease and you're done. You don't have to do any additional tests. So this is going to save you n-1 tests if n is the number of people that you're pooling together. Of course, if it's positive, it requires an extra test, n+1 test total. But the idea is that you're hoping that enough of these pools will come out negative that you save yourself a lot of antibody tests. So the question we're going to try to answer this week is if a particular disease has a prevalence of 10% in a population, can you use this strategy to save yourself tests? And if it turns out that this strategy will be helpful with a 10% prevalence, what's the optimal number of samples to pool per lot? How many people do you need to pool at the same time to optimize and minimize the number of antibody tests you have to use? Because of course, if you pool too many people, everybody will turn out positive. If you start to pool too few, you're not going to save as many tests. So we're going to try to answer that question in an upcoming module. I'll challenge you, if you're somebody who really wants to be challenged in this course and you like these types of problems, I did give you some tricks of probability last week that are probably sufficient for you to be able to answer this question right now. So it's a tricky question. It's pretty challenging, but if you want to challenge yourself, you could try to tackle this before we get to the module where I'm going to go through the answer. The third little teaser for this week, I'm going to give you a particular problem right now, but actually the thought process underlying this particular problem has a wider application in statistics. So this is really generalizes to a whole set of problems. But here's the fun example. Imagine you've got an anti-aging treatment, and you want to test whether it improves wrinkles on people. So you do a small study. You treat 10 patients with the anti-aging treatment. You photograph them before the treatment and after. One way to evaluate whether or not there was a visible improvement in wrinkles is to take those photographs and have a blinded independent dermatologist view them and just have that dermatologist try to order them pre and post to try to figure out which one is the before picture where presumably the wrinkles are worse and which one is the after picture where the wrinkles are better. And let's say you do that experiment and the dermatologist gets 9 out of 10 subjects right, is correctly able to order pre and post for 9 out of the 10 subjects. Is that sufficient evidence to make you believe that the anti-aging treatment is actually doing something? Now notice this is a small study, it doesn't have a control group, but within the confines of the limitations of this study. So we're going to try to answer that question, and notice that it's only 10 subjects here. Just if the dermatologist was randomly guessing, had no idea which was pre or post, couldn't tell the difference at all, you would still expect them to get about 5 out of 10 subjects right just by guessing, right? So what we're going to try to do here to answer the question of whether or not the anti-aging treatment might be doing anything, we're going to answer a particular question. We're going to say, if the anti-aging treatment is completely ineffective, what's the chance that the dermatologist could have gotten at least 9 right purely by lucky guessing, just by randomly picking them out? In other words, if we could answer that question, that will give us some feeling as to whether or not this is something real going on with the anti-aging treatment or whether this is just the dermatologist got lucky and was able to do 9 out of 10. Is that enough, 9 out of 10, is that enough to give us a sense that there's really something going on here? So we're going to answer that question in an upcoming module.